Good evening, class. This is practice test number 2, module 2, covering chapters 4 and 5. Here's chapter 5, discrete probability distributions. Does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? So the table is given. In the case of a discrete probability distribution, you have a table, X and P of X, the probability. So the variable X, which is the number of girls in 3 birds, 0, 1, 2, 3, is a numerical random variable, and its values describe probabilities. Number 2, summation of a P of X. Here's the P of X. Summation of P of X means add them up. So 0.125, 0.375, 0.375, 0.125. When we add them up, this must be 1. Summation of probability is always 1 or 100%, or a number extremely close to that, because sometimes due to round off error, they may end up being 1.0000001 or 0.9999, many nines. In other words, the number must be extremely close to 1. If we have exact answers, it will always be equal to 1. And each value must be between 0 and 1. Can it be 0? Yes. Can it be 1? Yes. But it can't be negative, and it can't be larger than 1. That is extremely important. So we have a numerical value. The sum is 1, and each one must be between 0 and 1. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, numbers go from 0 to 9, therefore there are 10 digits, 10 possible numbers in 4 different places. We can repeat the numbers. There is no restriction. We can multiply 10 by 10 4 times, or it becomes 10 to the power of 4 equals 10,000. So there are 10,000 possible outcomes. What is the probability of winning? Probability of winning is described as n of winning over n of s. We have total of 10,000. How many different ways can we win? There's only one way. So 1 out of 10,000. If we select the correct 4-digit number, there's only one way. If you win, what is your net profit? Net profit is the amount of money we collect minus the amount of money we paid, the cost. We collect $3,000 if we win, but we paid already 60 cents or $0.6. So the net gain will be $3,000 minus 0.6, which is $2,999.40. We want to write the probability distribution of net profit if you win. So we have to have a table like that. We have numbers here, net gain here, and the probability, the numbers over the total. So for the $3,000 winner, there's only one possibility. Then the rest, everybody is going to lose. And we have a total of 10,000. So this is one, this is 10,000. The rest of it, 10,000 minus 1 or 9,999 goes here. All right. What is the net gain? Well, for the winner is this much. We calculated it. What about everybody else? Negative 0.6. It's negative for everybody else. And that's extremely important to pay attention to. Minus. The dollar amount is positive here. The dollar amount is negative here. Now, what is the probability for this case? How many ways can we win? Just one way over the total of 10,000. So this would be 1 over 10,000. What about this one? 9,999 over 10,000. So I hope everybody can see how we calculate those numbers. Again, the number, whatever you see in the first column, divided by the total. This is called the probability distribution, in this case of net profit. Let me quickly fix this for you. All right. The next part is to find the expected value. So we have this table from the previous page, and we are told to find the expected value and do the interpretation. The expected value is defined as summation of x times p of x. Summation of x times p of x. So what does it mean? That means x sub 1, p sub 1x, x sub 2 times p sub 2x, and so on and so forth. So you multiply this column by this column. So you multiply these two numbers. So that's what we are going to calculate, x times p of x. This is x, this is p of x from the previous page. Multiply these two numbers, write it here. Multiply these two numbers, write it here. So when we multiply these two numbers, we get 0.29994. When we multiply these two numbers, we get negative, and pay attention to the sign, negative 0.59994. Mu is the summation of x p of x. Mu, or the expected value, is when we add these two numbers. So when we add the two, they add up to negative 0.3. So again, pay attention to the sign. Very carefully, we end up with negative 0.3. To do the interpretation, I want to continue and calculate the variance and then the standard deviation. So the variance is summation of x squared times p of x minus mu squared, or the summation of x minus mu quantity squared times p of x, and sigma would be the standard deviation, which is the square root of that. To calculate this using this formula, x squared times p of x. Here's x, square this, using a calculator, square this, multiplied by this. put it here. Then square this number, multiplied by this, and put it here. So this is x squared. So we have mu, we already have that. So when we square this number and we multiply it by this, it gives us 899.64004. I like to carry out a bunch of decimals. You follow the number of decimals they ask you to do so. Then when you raise this one to the second power, remember it's x squared p of x, this becomes positive and times this number, we end up with 0.359964. So again, square this column, multiplied by this column, put it here. So the summation of x squared p of x, just adding them up, if we add those two up, we get 900. But to find the sigma squared, which is the variance, we got to subtract the mu squared. In other words, square this one, subtract from this one becomes sigma squared. When you take a root, becomes sigma over the standard deviation. So in one shot, I'm going to take a root. I'm going to use this formula sigma versus sigma squared. Everybody pay attention to this is the variance. And this is the standard deviation. All of these formulas, you have access to it, obviously. And so we calculated this part to be 900 minus, we have the mu, we're going to square that and subtract it from 900 and take a root. And we end up with 29.9985, almost 30. So this is the interpretation. Everybody who plays is going to lose an average of 30 cents or $0.3. Why? Because it's negative. With the standard deviation about $30. So on average, a player, all players, including the winner, on average, and that's the key, loses this much, $0.3. If it was positive, we would say would gain this much, would win this much, which means 30 cents per ticket. With standard deviation, this is almost $30. That's the interpretation. Could somebody read this question, please?
A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. A particular shipment of thousands of aspirin tablets actually has a 5.0 rate of defects. What is the probability that this whole shipment will be accepted?
So this happens a lot when companies receive shipments, different types of shipments. They don't have time to check everything, but they sample, and if they sample properly, they can come up with a decent answer. So in this case, we are dealing with tablets that are either they have a defect, they are defective or not. That means we are dealing with a binomial distribution where we have 2 outcomes. So whenever you deal with binomial distribution, there are 2 things you need to know. What is n? 24. What is a p? P is called the probability of success, and it is important to know it doesn't mean anything. It could be positive, it could be negative. Of course, defect is a negative concept, but that's fine. So P is 0.05. So again, this is BD, short for binomial distribution. Anytime you claim you have a binomial distribution, You got to be able to provide two things for your reader. What is n? You have 24 tablets. Randomly select 24. What is the probability that it's going to be defective? 5% means 0.05. So first, what is a binomial distribution as far as the formula? P of x is n factorial over x factorial times n minus x factorial, p to the power of x, q to the power of n minus x. Now again, you have this formula, and this is combination of n choose x, p to the power of x, q to the power of n minus x. Mu, the expected value is n times p. Sigma, the standard deviation is square root of npq, and q is 1 minus p. All right, so this is the synopsis of what you need to know to move on. So let's look at the definition of a binomial distribution. Binomial experiment and probability distribution, PD, probability distribution properties. First and foremost, we have n identical trials. Each repetition of the experiment is called one trial. Each has precisely two outcomes. Either it's defective or not. Two outcomes, tails, heads, things of that nature. Probability stays constant. So one tablet compared to the other one, they have nothing to do with each other. It's independent. So the probability stays constant. The 5% doesn't change, and they are independent. So let's quickly recap. We said it's a binomial distribution because there are only two outcomes, whether the tablet is defective or not. N is 24, P is 0.05, and here's the formula. Let's plug in. So we are going to use this formula where N will be replaced by 24, P will be replaced by 0.05, and Q is 1 minus that. What is 1 minus 0.05? Is a 0.95. So P is 0.05, Q is 1 minus P or 0.95, and N is 24. Let's plug it in. That's the formula in general. Now, what are we looking for? The entire shipment is accepted if at most two tablets do not meet the required specifications. So if the probability of X is less than or equal to 2, that's the meaning of at most 2. Probability of X less than or equal to 2. That means in this formula, we let X be 0, we let X be 1, we let X be 2, and we add them up. In other words, probability of X equals 0, probability of X equals 1, probability of X equals 2. If we plug in 0 and then 1 and then 2, by the way, X equals 0, shorthand notation, just P of 1, and we add them up, we get this one. You don't have to calculate this by hand, but it can be done. Again, into this formula, replace the X with 0 gives you a number. 1 gives you another number, 2 gives you another number, add them up. However, we can use a calculator. For a binomial distribution, if you click on second and variables, you use binomial PDF, NPX, and you enter. If you enter only N and P, gives you all probabilities from 0 to N. And if you use binomial CDF, then it gives you the sum of the probabilities from 0 to X. So using the calculator for the trials, you put N, which is 24, you already have that. You put p equals 0.05, you already have that. And the x values, we said at most 2, we plug in 2. So it gives you this sum, because we are using CDF. It gives you the sum starting from 0 all the way to 2, and that's exactly what we want. And CDF 24, 0.052 gives you this answer. As you can see, this answer is the same as that one. So you can use a calculator to get there, but you really need to understand what you're doing, and that's why we dissect the problem by writing the given. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress? Again, we are dealing with BD, binomial distribution. Why is that? The managers either suffer from the stress or they don't. There are two outcomes. So what is N? 20. What is P? 0.7. So what are we using? The formula, again, you can find it in your formula sheet for the binomial distribution. We have N, we have P, and Q can be calculated as 1 minus P. So it makes it 1 minus 0.7, which is 0.3. So we have everything. We can plug into this formula, replace the N with number 20, P with 0.7, Q with 0.3. So again, step by step, into this formula goes N, so 20 factorial, over X factorial, times 20 minus X factorial, it's N, times P to the power of X is 0.7 to the power of X, times Q to the power of N minus X, Q is 0.3, N 20 minus X. Pay attention to the formula and how we plug it in. Exactly 8, your X is 8. Your X is 8. So if I plug in 8 instead of X, this becomes 8, this becomes 12, this is 0.7 to the power of 8, this is 0.3 to the power of 12. By the way, you can put it in any order, 8 factorial times 3 factorial or not. This because you can actually set it up. So remember what we did. Into this formula goes X equals 8. And now you can do the calculation. You can use the calculator. Either way is fine. If you use the calculator, you use PDF. Why do you use PDF? Because you are calculating it at exactly 1 point, namely X equals 8. So N is 20, P is 0.7, X is 8. It gives you this answer, and you write it here. Now, as far as the number of decimals, you should always pay attention to what they ask you. So you round it accordingly. We are looking at the same question, and part B says at most 8 suffer from job-related stress. At most 8, that means the probability of X less than or equal to 8. That means X can be 0, 1, 2, all the way to 8. That's the meaning of at most 8. So take a look at most 8 and what it means in math. Therefore, we have to use this formula, plug in 0, 1, all the way to 8, and add them up. In other words, we are looking for a probability of 0, 1, 2, 3, all the way to 8. Now, again, understanding it is what matters. At this point, obviously, if you want to calculate it one by one, it takes a long time. You are going to use a technology or a calculator. So n is 20, p is 0.7, x is 8. Remember, this is CDF, which is going to give you everything from 0 all the way to the number you pick here. And this is the answer. You put it here. And again, with a bunch of decimals. So since I'm stopping here and the next one is 6, I changed it to 2. Same question. At least 9 suffer from job-related stress. So we are looking for probability of x larger than or equal to 9, which means we want x equals 9, 10, 11, 12, all the way to 20. And we have to plug in 9 here, 10 here, 11, all the way to 20 and add them up. So there are so many parts to add up. So what does it mean? Find probability when x is 9 and x is 10 all the way to 20 and add them up. And again, you can use the technology. In this case, what is interesting is that probability of x larger than or equal to 9 means 1 minus probability of x less than or equal to 8. Probability of x larger than or equal to 9 means 1 minus the probability of x less than or equal to 8. And since you have this, simply 1 minus this number, which gives us 0.99486. So we need to understand the meaning of at most, the meaning of at least. We're going to continue with the same question. Find the expected value. And E is equal to mu equals NP. That's a formula that was discussed in the beginning. So plug in N, plug in P, 20 times 0.7. The answer is 40. The next one is asking for the standard deviation. Sigma squared is NPQ. Again, that's a formula. So N is 20, P is 0.7, and Q is 0.3. Remember 1 minus P, and you get 4.2 when you multiply. 20 times 0.7 times 0.3 gives us 4.2. What is standard deviation? This is sigma squared. This is the variance. It's the square root of 4.2, which is about 2.05. 2.05. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? Well, if you recall, mu plus minus 2 sigma is considered the usual, meaning starting from the mean, if you go 2 standard deviations to the right or to the left of it, it is considered usual, otherwise it's unusual. So mu minus 2 sigma and mu plus 2 sigma must be calculated. We have the value of mu to be 14. So minus 2 times this number and then plus 2 times this number. So 14 minus 2 times 2.05 and 14 plus 2 times 2.05. So So you subtract 4.1 from 14 and you add 4.1 to it, gives us 9.9 for mu minus 2 sigma and 18.1 for mu plus 2 sigma. If the 7 is an element of that, it's usual, otherwise it's unusual. 7 is not an element of it. This is where we are looking for. 7 doesn't belong there. The notation in set theory, this class is read not an element of. If we had it without this line, would be an element of. 7 is not in between. If it were in between, would be usual. Since it's not, it's unusual. Find the probability of a couple having at least one girl among 3 children. Well, there are different methods of approaching this. The first method, we're going to look at the concept of at least, which is 1 minus probability of none. So probability of at least 1 equals 1 minus the probability of none. And in this example, notice that probability of G girl equals probability of B boys. It's 50% or 1/2 or 0.5. At least that's the assumption. So it will be 1 minus probability of no girls. Remember, the probability of boys would be 1/2. So 1 minus 1/2 to the 3rd power. That means this means all boys. Probability of one boy is 1/2. The second one, 1/2 times 1/2. The third one, 1/2 times 1/2 times 1/2, or 1/2 to the 3rd power, which is 1/8. 1 minus 1/8, this is 1/8, everybody. So the answer is 7/8. So that is the first method. We use the probability of at least 1 equals 1 minus the probability of none. The second method, we use binomial distribution, in which case, what is n? N is 3. What is p? Probability of girl. That's what we are looking for. It is 50% or 0.5. What are we looking for? At least one girl. That means X can be 1, 2, or 3. So we want probability of X larger than or equal to 1. So can we have 1? Yes. 2, 3, and the P and Q happen to be equal to each other. Both of them. 1 minus 0.5 is 1/2. So Q is also 1/2. So what we are looking for is the probability of a 1 plus probability of 2 plus probability of 3. And again, you have to calculate them one by one and add them up. But it makes it easier if we go with 1 minus probability of 0. And here's the formula: n factorial over x factorial, n minus x factorial, p to the power of x, q to the power of n minus x. So what is n? We're going to replace the n with 3 here and here. What is p? 0.5. Q happened to be 0.5 also. So we plug it in here. If we want to go with this route, we're going to plug in 1, calculated, 2, calculated, 3, calculated, add them up. Instead, we are going to calculate, just plug in 0 and calculate it, and subtract it from 1. So replace the x with 0. Wherever you see x, replace it with 0. 0 factorial is 1. This becomes 1.5 to the power of 0 is 1. So it becomes 0.5 to the power of 3. So I hope you see that this is 1. So is this one. So this is the answer. Also, what I want you to, so it becomes 1 times 1 times 0.5 to the power of 3. Also, I want you to note, this is extremely important. Because they are the same, probability of G and B are the same, it seems that we are just using this P to the power of 3. That's not what we are doing. We are really using Q here. It's important to know this is Q, not P. It happened to be equal to P. So I'm going to make it so you can see that this is Q to the power of 3, because they may not be identical. So probability of X larger than or equal to 1 becomes 1 minus 0.5 to the third, which is 1 minus 0.125, and we get the same answer as before, this one. So there are different ways of approaching that. If an alarm clock has a 0.9 probability of working on any given morning, what is the probability that it will not work? We simply use the complementary event. Probability of working is 0.9. Probability of not working is 1 minus that. So probability of working is given as 0.9. I'm going to use W to represent working. Probability of W not, look at this one, the complementary event. So not working would be 1 minus that, which is 1 minus 0.9, which is 0.1 or 10%. And that's horrible. 10% chance that it's not going to work. That's really bad. But here's what's interesting. What is the probability that 2 such alarm clocks will not work? Now it's the concept of redundancy and equality control, and that's what companies use. Even if the percentage is that bad, when you have 2 alarm clocks, then things are different. How do we calculate that? Probability that the first one doesn't work, we call it probability of W sub 1. The first one is not going to work. It's going to work. The probability that the first one doesn't work, we put a bar at top of it. So W sub 1, the first one is working, probability of one of them is working. W1 bar, it's not working. So what do we want for part B? We want the probability of W1 bar intersection W2 bar not working. And so basically we are assuming independency. So we are looking at the probability of the first one and the second one not working. And they are independent events. We simply multiply the two. Each one has a 10% or 0.1 probability of not working. So this is 0.1, so is this one, and their product becomes 0.01. So as bad as this 10% is that one won't work, if we have 2 of them, there is a 1% probability that 2 such alarm clocks will not work. Both of them will fail. That's the idea. Needless to say, if there is a power outage, that's when they become dependent. Then they both will stop working. Other than that, they are independent. So we're going to continue on that thoughts. In the last part, what is the probability of being awakened if you have 2 such alarm clocks? Clearly, just one, we had a probability of not working was 0.1, working was 0.9, and for 2 of them not to work is 0.01. So that's what we have already. And so 1 minus that, the probability of being awakened is 1 minus not working. Assuming that we wake up to the alarm clock, there's a 1% chance that it won't work. So 1 minus that, 1 minus 0.01 is the probability that we're going to wake up. So that gives us 0.9 That would be the percentage. 99% probability that we will wake up. The second method is called the addition method. Probability of A union B is probability of A plus probability of B minus the probability of A intersection B. We had discussed this before. So the probability of a W1 union W2, that means the first one working as well as or the second one working. The first one or the second one working. Following this formula is probability of W1 plus probability of W2 minus the probability of W1 intersection W2. Each one has a probability of 0.9. So this is 0.9, this is 0.9. And their intersection, we just multiply. We've already done that for not working. For working, we do the same thing, 0.9 times 0.9. So this is 0.9 plus this is 0.9, and this is minus 0.9 times 0.9. And we get to the same answer. 0.9 and 0.9 is 1.8. This is 0.81, by the way. This is 1.8 minus 0.81, and we get the same answer. There's a third method. I want you to be exposed to all ways that we can handle this. It's a binomial distribution simply because there are two outcomes. It will work or it will not. How many alarm clocks do we have? 2. What is the probability that it will work? 0.9 or 90%. So what formula are we using? P of x is n factorial over x factorial, n minus x factorial, p to the power of x times q to the power of n minus x, where n is replaced with 2, p replaced with 0.9, and q is 1 minus that, or 0.1. So we replace them accordingly. Probability of x larger than or equal to 1 is 1 minus probability of 0. Again, you have a choice that you plug in 1 here and 2 here and calculate this left side, or it's easier to plug in 0, calculate it, subtract it from 1. It has less calculation. So 1 minus, replace the x with 0. When you do that, this becomes 2 factorial over 2 factorial, which is 1. 0.9 to the power of 0 is 1. So 0.1, this is what I meant when I put it last time. Q is 0.1 to the power of 2. So this is 1. This is 1. This is 1. And this is 0.1 to the power of 2, which is 0.01. 1 minus 0.01 is the answer, which is 0.99. Could somebody read this, please?
During the NFL season, there was 256 games played with 1,307 touchdowns scored. What was the mean number of touchdowns scored in each game during the season? Round the answer to the nearest.
Excellent. So we have something called Poisson distribution. The probability of the event occurring x times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by probability of x is mu to the power of x, e to the power of minus mu over x factorial, where e is 2.71828, and it continues indefinitely. It's the base of a natural log, everybody. Mu is the mean number of occurrences of the event in the intervals, and the parameters mu and sigma, both of them, have the following situation that sigma is the square root of mu. Sigma equals square root of mu. So in this case, we have to calculate the mu and the mean number of TDs, touchdowns, in each game. The mean or mu is the total number of touchdowns, 1,307, over the total number of games, so 256. So when we divide the two numbers, it gives us 5.105469. We can go with a few decimals. And what it means that on the average, each game had this many touchdowns. And I want you, although the number of touchdowns is a discrete value, but because you're saying on the average, you can go with decimals. It's like, can you say a household has 2.5 cars? No, but you can say every household in some neighborhood has an average of 2.5 cars. That we can say. So with that being the case, we have the value of mu calculated. And we use the Poisson distribution mu to the power of x, e to the power minus mu over x factorial. And we replace the mu with the number we just got. I rather keep the e as e instead of that number because that gives you a more precise answer if you use a calculator. Again, 2.71828, and it continues indefinitely. So that's the Poisson distribution as a result of this. Now, on January 10th, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were how many touchdowns? A lot more than this average, 13 touchdowns. What is the probability that a random game would have that many or more touchdowns? In other words, we want the probability of x larger than or equal to 13. That's what we are looking for. Now, clearly, what this means if we want to calculate it just the way it is, into this formula, we put number 13 instead of x, calculate it. 14, 15, all the way to sky's the limit. So what do? Instead, we use the complementary event. This is 1 minus the probability of x less than or equal to 12. So this is the way to calculate this. Again, nobody expects you to do this by hand. This means the probability of x equals 0, plug in 1, 2, all the way to 12 and add them up. That's the meaning of this. But we can use technology, second variables, Poisson PDF. You put mu, sometimes they call it lambda. This is mu, this is lambda, depending on the text. X, enter or paste. If using Poisson CDF, it gives you the sum of the probabilities from 0 to x, just like a binomial distribution. So we use Poisson CDF and lambda, which is the mu that we came up with, is 5.105469. You probably want to write this value because you want to give it a lot of decimals. The x value all the way to 12, and paste it, you get this number. And this must be subtracted from 1. Subtract this number from 1. So 1 minus that gives you this answer. And we write it as 0.0024. We sort of stop here because of 4 decimals that they mentioned here. This is the main part of the question. The first column lists the number of touchdowns, 0, 1, 2, 3, so on and so forth. This is filled in already. We want to go with a few. The second column is for the predicted probability, and we use 4 decimals. That a game chosen at random will have that many touchdowns. Calculate them, okay. Round them using this, that means 4 decimals. And the third column is for your best prediction about the number of games during the season that had that many touchdowns scored. Round these values to the closest whole number. First and foremost, I want to write what we had from the previous part, so we know that. In this case, it says when it's 0, just plug in 0 and calculate that. I want to tell you what each one is. So let's look at 0. When you plug in 0, by the way, this is 1, it means e to this power. If I just use e to this power, I get this number. If I use Poisson distribution with this number for mu or lambda, and the value is 0, notice, of course, I get the same, okay? I get the same. Then why am I multiplying by 256? Because of the third column, the last column. The third column is for your best prediction about the number of games during the season. So for 0, the probability is this much. So we have 256, we're going to multiply it by 256. So this number comes from here or here. This number is the product of this and 256, which is this number. Now, this must be rounded. How? Accordingly. 1.55 when you round it becomes 2. Just accordingly. Now, for the next one, we use number 1 in this formula, and we use a calculator to do the math. Whatever the answer is, we're going to multiply by 256 to come up with the next one. So if I go with the second one and use 1, I get this number. If I multiply it by 256, I get this number. So I put this number in front of 1.03095 and so many decimals. And then this number 7.9, and this gets rounded up to 8 also. The next one, so I calculated the 1, I calculated the 2, and I'm going to multiply it by 256, and I get those. So take a look at what happens. So this is the next one, everybody. This is the next one, and I put continue. You can continue on that thought. This number goes in there, 7.925, and you have to round it. This number goes in there. Now 20.23, when you round it, goes down to 20 because you're looking at this number, and you want to answer it discretely, this last column. The main part that I'm interested in understanding why Poisson distribution and how we can calculate this probability.